All right, so today we'll just do a quick workshop on amino acids. And as we consider amino acids, we're thinking about basically our protein building blocks for life. So there are 20 so if we think about amino acids, right, there are 20 amino acids occurring naturally in nature. Right, so there are 20 amino acids in nature. Humans can make 8. Humans can synthesize 12. So our bodies can make 12 of these amino acids. The other 8 are called essential amino acids. So the other 8 amino acids are called essential amino acids. And that just means that they're essential because we can't make them. Right? So since your final is open, I think your final is probably open note. You technically don't need to memorize the amino acids. You just need to be familiar with them, be able to draw them quickly if you need to. But our general amino acid form needs to have a carboxylic acid part, right? It also needs to have an amine part of the molecule, and then there'll always be some R group present, right? So that's our amino acid. And our amino acid can also exist as a Zwitter ion. So if you think about just having a proton transfer, this is an equilibrium, right? We can have our deprotonated carboxylic species, and we can protonate our nitrogen. So now this nitrogen gets 3 hydrogens and a positive formal charge, and we still have our R group there, and this would be our Zwitter ion. I don't know why I drew an S. R, and this would be our ZWITTER ion, right? So we have our Zwitter ion, and it has positive, and so our Zwitter ion has positive terminal, which is our nitrogen containing terminal, and then there's also a negative terminal or negative side, which is our carboxylic acid COO minus terminal, right? So our N plus and COO minus, that's for our Zwitter ion, and then we can also have our neutral amino acid. And what determines the amino acid structure in aqueous solution in water is our pH. So pH determines amino acid structure. Right, so if we think of an amino acid where we have, let's say we have N, and then we have CHH, COOH. So I'm just using a really simplistic amino acid H2, right? We can get a positive charge on our nitrogen, and this will be the form that is predominant at low pHs. So at pHs that are less than 1, this would be our acidic pH, right? And then you can imagine that there's some equilibrium. If we get to a pH that is around 6 or 7, our neutral pH, this is where, for this specific amino acid at least, this is where our Zwitter ion exists. So it would be N, and then there should be H2 with a positive formal charge, right? Oh, sorry, this shouldn't have a hydrogen. Yeah, okay, yeah, so that would be our Zwitter ion. And then when we get to so basically you're thinking about removing a hydrogen at a time. So with our pH, with the pH that's acidic, we have lots of protons and a positive charge. At our pH around 7, we have our Zwitter ionic form. And then when we get to our basic pH, which I'll actually draw down here, we lose a hydrogen on our nitrogen, and CH2, COO minus, right? And this predominates at a pH that is greater than around 13, right? So that's where these ranges kind of occur. And the way that I like to think about it, right, is that our protons, H plus, are positive. Our base, OH minus, is negative. So that's how I kind of remember our pHs. And then when we want our neutral molecule, we can imagine that our positive and negative charges cancel each other out on the Zwitter ion. All right, any questions about that? No? Right. So another thing that you'll need to know how to do is to calculate the isoelectric point. So the electric point is specific to an amino acid, right? And it's a neutral pH for each amino acid. It's the pH where the neutral form dominates. And the way that we'll calculate the isoelectric point is we want to look at our amino acid, and if there are no ionizable groups, we'll just take the average of the two pKa's of our amino acid of our different sites. If we have more acidic chains, we'll take the average of our two lowest pKa's. And if we have basics, then we'll basic chains on our amino acid, we'll take the average of our highest pKa's. So that's kind of a verbal way to describe it. Now let's go to the workshop and try that out first, right? So in example 2, we want to determine the pH for the following amino acid where it exists at a Zwitter ion, which is the isoelectric point, right? So the isoelectric point is our Zwitter ionic value. So we want to get the pH for that. And the way that we can do that is we'll look at the pKa's, and in this molecule, you'll see that we have, in this case, if we were to highlight, we can see that we have 3 pKa's given. One for our COOH, our carboxylic acid group, one for our basic NH3 terminus, and then another one for the nitrogen on our side chain, right? So if we consider our side chain, then all of this is considered to be the side chain of our amino acid. So you'll notice that on our side chain, we have a high pH, right? It's 12.5, which means it's basic. So what we want to do to calculate the PI is we want to actually select the pHs that are closest together. So 2 of the pHs that are closest together is how we'll calculate our PI. So in this case, our PI should be equal to 9 plus 12.5, and we want to take the average of these pHs, or of these pKa's, right? So that would be 10.8, right? So this means that 10.8 is our PI, and we can also say that our pH, where the amino acid exists as a Zwitter ion, will occur between a pH of 9 and 12.5. So it's going to be in the range between our closest pKa values on our molecule, and these have to be given to you, right? There's no way you can take the average if they're not given to you and you don't know them, so you just have to figure that out. Okay,